Hello, and welcome back to our topic 4 applications of derivatives, continuing our journey throughout AP Calculus AB. At this point in time, you should be pretty comfortable with the first derivative. And so today we're going to move on to further derivatives and discuss what they measure about a graph, how they relate to the first derivative, all that fun stuff. But let's start us off with a nice geometry review. Yes, we have to do a little geometry here, but it's nothing too terrible. So quick opener, you're going to have to sketch a regular convex polygon. You might have to look that up. A concave polygon, not necessarily regular here. That's a little trickier. And then go ahead and discuss what you know about the word concavity and convexity of a graph. So again, take a minute or two, try those. It's not crazy important if you do it right or not, but you can always do your own research. And then whenever you're ready, please unpause and we'll get rocking and rolling. Alright, so hopefully you remembered that a regular polygon is one where all of the angles are equivalent and all of the sides are congruent or equivalent as well. So polygon means many sides, often confused with pentagon, which is 5 sides. So I'll draw a regular or an approximately regular hexagon, something like this. I'm sure it's not perfect, it's definitely not perfect, but there's my regular convex polygon. In this case, it's a convex hexagon. And then I will sketch a concave hexagon as well, and it's going to be very, very similar. I'll even start it off pretty much exactly the same, something like this, and then we're going to make it. Oh, I should have done one fewer, huh? That is one too many sides, but that's okay. You get the idea. We have this concave polygon, which oftentimes is defined as this angle inside is, greater than 180 degrees, something like that. But we can see the difference, and I bet you learned a cave is where something caves in versus a convex has that outer bulge, right? This is bulging out to the side instead of caving in. So you may not have heard before, though, these concavity and convexity, so these adjectives describing our graph, right? So what does it mean for a graph to have concavity or convexity? You can use both. Well, they kind of measure the same thing depending on how you look at it. So calculus is really just going to talk about concavity. You can talk about convexity, but concavity is essentially how much a graph is bowed inwards, right? It makes a cave. Versus convexity would be the same thing, but it's bowed outwards. So again, if I had some sort of graph, and I don't know, let's say I have a line, right? And then the line kind of drops in like that and then continues. We would discuss the concavity of the line, this cave. Of course, if you're looking at it from the other side, you're like, well, what about the convexity, kind of the push out part instead of the push in. But yeah, we're picturing like we're pushing in this line. And I really like to think of concavity as more like curvature of a line. So if you're just thinking about I almost said a straight line, and I always make fun of my students. They're like, well, what about a straight line? I'm like, what kind of line isn't straight? So how about this? A diagonal line. This line has no curvature. There's no bulge in it. So this line would have 0 concavity, also 0 convexity. But again, that's the last time I'm going to mention that. We'll just focus on concavity. This has 0 concavity, and the more curvature it gets, the more concave it gets, the higher the degree of concavity. Very, very similar to slope. Slope measures the steepness of a graph. Concavity measures the curvature of a graph. Now, visually, concavity is really easy to see. So we're going to go ahead and just list some intervals on which the graphs below are concave up and also concave down. For example, if you pictured this original graph as just a straight line across, what had to happen to turn it into this parabola? Well, someone had to push this piece here, and so it's going to, look like this. Of course, it kind of, I could totally understand you saying, well, wait, doesn't that mean it's concave down because we had to push this part downwards? And yes, I get it, but we've decided that this means concave up. So this whole graph, because in Algebra 1 you learned that it's opening upwards, facing upwards, something like that. Really, we should introduce concavity earlier, but that's fine. Because this whole graph is facing upwards, the whole graph is concave up. And so you could go from -2 to 2 because there's no arrows there. You could say negative infinity to infinity. I'll just use -2 to 2. We'll pretend that they're like actual closed end points here. So we're going to say it's concave up from -2 to 2. Of course, we'd have to have that same conversation as we did with increasing, decreasing. Do we include the endpoints? Do we exclude the endpoints? And I'd say for now, include them. It's totally up to you. Strangely, I tend to exclude the endpoints here, and I'll talk more about that later on. But either way, nothing too bad. Where is it concave down? It's concave down nowhere. So you could use this empty set for an interval, right? This isn't 0. 0 is the point right here. This is null. This is the empty set. Sometimes you'll see it written like that. There is no place where our graph is concave down. Compared to our second one, I bet you can see that the right side of this graph looks just like our parabola. This right side is where my graph has positive concavity, or where the graph is concave up. And so we'd write that and we'd say the graph is concave up from 0 to, and I said I'd use 2, so we'll continue to use 2. Where is the graph concave down? Well, I bet you can see that it's concave down right over here. And so we'd say -2 to 0. Nothing too bad. So knowing that, then, why don't you bring that knowledge to this last graph? It has a whole bunch of different points on here, and see if you can determine where the graph is concave up versus concave down. And be careful, because concave up, concave down is not the same as slope, right? This graph is increasing everywhere. F prime is positive all the way through, but there's two different concavity intervals. So keep that in mind. See what you can do with this last one, and then unpause me to hear my soothing, sonorous voice come back and talk you through concave up and concave down. All right, I'm going to continue to use green for concave down and purple for concave up. You might notice that this all looks like a parabola really till about here that's facing downwards. Then my parabola shifts to being concave up until here. Sorry, I should zoom in. Then concave down. I said switch colors. Concave down, lovely. And then it looks like at the end here we are concave up all the way through the end part. Okay? And you might notice something where this graph is changing concavity too. Where the graph is changing concavity, right? These points kind of in the middle, yeah? That's, if you zoom in, really the closest spot to where the concavity or the graph looks like a line. And so that shouldn't shock you that basically what's happening is we have lots of concavity here, but as we approach the shape of a line, the concavity is decreasing or increasing, depending if we have negative or positive concavity. We'll get into that. But the graph is approaching the shape of a line. And we discussed up above that a line has 0 concavity, 0 curviness, right? So we take extreme curviness down here, and we approach this 0 curviness over here. So we might want to start thinking about the places where concavity changes as the places where our graph has a concavity of 0. All right, now I'm not going to write the intervals. I assume you're fine with those, and there's a bunch of numbers on here. You'll probably recognize these maybe as some trig functions, right? That might be some pi over 4.707, very, very common. Might be root 2 over 2. I actually don't remember which one. But yeah, I recognize that 0.707 from trig. So my guess is they use trig functions to create that graph. I cannot take credit for it. But let's go ahead and get on to our follow-up questions. Question 1, do we include the endpoints of our concavity intervals? Why or why not? I'm actually going to come back to this one once we define concavity, so remind me if I forget. That's a joke. I hope I don't forget. You can tell me on the YouTube comments if I do. And then part B is a really interesting one, and I'm not going to answer part B. I'm going to let you answer that because it's kind of that similar situation where we struggled to describe relative mins and maxes. Defining concavity is tricky. Right? When I said it measures the curviness of the graph, that's not a very mathematically strict definition. So how would you define it? I mean, can you relate it to slope, to calculus, to something outside of calculus, whatever sounds good to you. So see if you can think of a fun way, and if you do think of a fun way, let me know. But hopefully you've had time now to describe that concavity again. I'll get back to those endpoints, but let's go ahead and define concavity in one way that we've kind of ignored for a couple classes. It's been very rude of us, but we're coming back to them. So one way we can define concavity is using our old friend tangent lines. You're like, what? Why would you use a line to define the curviness? Well, imagine if we found an interval where all the tangent lines lie below a graph. In fact, let's use this graph over here on the previous page. You don't need to turn the page, nothing too terrible. And I'm going to use the blue line to represent a tangent line. Well, if you start writing a few tangent lines, for example, if I do one tangent line, and this always looks weird with a graph because I can't really zoom in super far, you lose sight of the graph. We call this a tangent line, and we start thinking in terms of above and below the original graph, then we're really going to be comparing the outputs, the y values. So what if I looked at the y value here versus the y value on the corresponding, the same x value, but the corresponding y value on the original graph? Well, you'd hopefully say that the y value on my tangent line, on the blue line right here, is higher or above the one on the red graph. In fact, anywhere you pick on this tangent line, you'll notice that the blue tangent line's y value is above the original graph's y value. And if I drew another tangent line, I'll do it in blue, something like this over here, you'll notice that that same pattern happens. Whatever y value you pick on your tangent line is above the y value on the original graph. So we would say that the tangent line lies above the graph of f, or above the original graph. But as we keep writing tangent lines, you'll notice that I'm not going to write a tangent line over here. The tangent line has to switch to becoming below my graph on this side. And now you'll notice that when we compare the y values of the tangent line are always below the graph. You can even do one more over here. It kind of gets tough to see when we have a steeper tangent line, but you can still figure it out, right? You see those two y values, the one on the tangent is below, or if we look at another one over here, the tangent is below. So describing concavity using tangent lines is a very, very common method where we would say anytime that the tangent line lies below the graph of f, that is equivalent to when the graph is concave up. And so that's actually what we have down here. Given an interval where all the tangent lines lie below a graph, we say the graph is concave up, which is somewhat surprising. You're like, wait, below but up? And yeah, so it really helps me, I sometimes don't remember this honestly, to draw some very generic concave up and concave down graphs. And the most commonly used ones are just the parabolas y equals x squared. So here's one parabola, and for a concave down, y equals negative x squared. These do a really nice job of illustrating a graph that is concave up everywhere and concave down everywhere, right? There's no place that switches concavity. Don't think that this spot is zero concavity either. That's just zero slope. It's slightly different. It is quite curvy. And so if you, again, think about those tangent lines, and you might want to draw a couple of these on your paper too, you can see that all of the tangent lines on here lie below the graph. However, if you can find an interval where all the tangent lines lie above a graph, then we say that graph is concave down, right? Here is a concave down graph. We can see that visually. And any tangent line you draw is going to be, oh, that was a terrible tangent line, don't judge me too much, is going to be above the graph. Now, it'd be pretty obnoxious if we'd had to draw a graph first just to see if the tangent lines were above or below it, and then how do we decide where the tangent lines stop being or start being above and below? How do we decide where the concavity switches? So we're dealing with differential calculus, and sometimes you'll hear calculus split into two fields, especially in AB. There's differential calculus, which is calculus with derivatives, and then next semester will be integral calculus, which is calculus with integrals. So since this semester is all about differential calculus, it shouldn't surprise you too much then that the answer to determine where graphs are concave up and concave down have to deal with slope, with derivatives. Okay, so let's go back to the tangent line. Right, our tangent line is based around a single point with a definitive slope. And so we can use tangent lines to find the slope at different points on the graph, right? So if my tangent line, I'm going to use the blue one because it's a little bit better. If we look at this slope here, right, the tangent line has the same slope as my graph versus this point versus this point. Yeah, we can use those to figure out the slopes of the graph. Now, if the graph is concave up around a point of tangency, let's see what we can conclude about the slopes of the points as we move from left to right. So that's a little vague, so we need a picture here. So for example, if I do one more tangent line, it's going to be really tough to see. I think you'd agree that this is a tangent line with a very negative slope. And I'm just going to make these slopes up. So very negative, let's call it negative 50. Maybe it's negative 10, I don't know. But very negative because it's steep, but in the negative direction. But then as we get closer down to, and I'll even draw one more right here, as we get closer to the vertex of this graph, the slope is still negative, but it's not as negative, right? In this case, maybe this is a steepness of like -4. And then if we get to the perfectly flat spot, there's a slope of 0. And then as we move to the right, now our slope is positive. Maybe this is a slope of 1. I don't know. And then as we keep moving right, yeah, we're moving from left to right over here. That's how we read pretty much anything in math these days, left to right. Maybe this slope is, I don't know, 20. It's not quite as steep as the other one. Well, what's happening with the slopes? We went from -50 to -4 to 0 to 1 to 20. Would I be wrong to say that the slopes are increasing in value? Right? Don't say, no, -50 is bigger. No, -50 is very, very negative, right? If you picture a number line, -50 is way over here, and every slope moves you to the right on a number line. So I think we'd say that the pattern of these slopes is that the slopes are increasing as we move from left to right. So the slopes are increasing. And in fact, this is a second way that we can define concavity. We say that a graph f of x is concave up on an interval where f prime of x, which again are the slopes or the derivatives of f, are increasing. Okay? And we also say that a graph, of course, is concave down where the slopes are decreasing, right? You'll notice that the first slope we get to is pretty positive, isn't it? Maybe we say that this is 20, and then this is much less positive. Maybe this is a slope of 1. Then right here again is a slope of 0. And uh-oh, now we're going negative. Maybe this is a slope of -2, and then way down here, even more negative, right? So our slopes are getting smaller or decreasing. That's what we just showed up there. Now, again, it would be somewhat obnoxious if we said, okay, we just want to find all the places where the slopes are increasing. And you take a derivative, and then you find like 50 different derivatives, and you're like, oh, the slopes are getting smaller here. Great. So then our graph is concave down because the slopes are decreasing. Well, let's use what we know about derivatives. F prime of x measures where a specific graph is increasing or decreasing. In fact, we say it measures where f of x is increasing or decreasing, right? That's what we've done the last couple days when we made a sign chart. We get a positive in the sign chart. That means our f of x graph goes up, which we say is increasing. So if f prime measures where f of x is increasing or decreasing, then what equation is going to measure where f prime is increasing or decreasing? Well, just thinking about the relationship, to find the equation that told us where f of x is increasing or decreasing, we took the derivative. So to find where f prime, where the slopes are increasing or decreasing, we again take the derivative. The second derivative measures the rate of change of the first derivative. Now, again, the rate of change is basically saying the pattern of the first derivative. It's telling us, are the values of the first derivative, which are, this is a little tough to keep straight, which are the slopes of f of x. It tells us, are the slopes of f of x increasing or decreasing? And that's actually really what we need to know, because a graph is concave up where f prime of x is increasing. And now we have a way to measure if f prime is increasing. Look at f double prime. So we can now redefine concavity and say that a graph f of x is concave up where f double prime, let's see, in order for f prime to be increasing, what does f double prime have to be? F double prime has to be greater than 0. That tells us that the pattern of f prime is moving in a positive direction. F prime is getting bigger because f double prime is positive, right? And you can even rewrite this over here and we can say that f prime is increasing. Versus a graph is concave down where f double prime is less than 0. That's where f prime is decreasing. Now, this seems a little bit complicated. You're like, wow, that was a lot of theory there. Shouldn't we get some practice? Yes, we should. I think we need one more thing before we get to our practice, and then you'll find that this is no harder than anything we've been doing so far. Guesses on how we figure out the actual intervals where f of x is concave up or concave down? Emphasis on intervals. Well, how did we find where f of x was increasing or decreasing? What intervals f of x was increasing or decreasing on? We made a sign chart with f prime. So if we want to figure out where the intervals are, where f prime, or where f is concave up or concave down, guess what we're going to do? Well, we're going to first figure out where f double prime of x is equal to 0, because when we found the increasing decreasing intervals, right, we started by finding critical points, and we call them critical points. And then after we found the critical points, we solved, of course, to find the critical points, and then we created a sign chart. And so f double prime's method, easy for me to say, to determine the intervals of concavity is the exact same process to determine the intervals where f is increasing or decreasing, except instead of using the first derivative, we use the second derivative. So let's rock and roll. Notice that this problem says examine the open intervals. So a lot of times they'll even tell you. They'll say use parentheses instead of brackets. If you forget and use brackets, they're not going to ding you, no stress. I think, say, though, that I would go back to this endpoints question, and so, let's do that. I'm happy that I remembered. Honestly, I forgot until we got to that question. So, do we include the endpoints? Why or why not? Well, I think there's a great argument to say that we do include the endpoints, because these endpoints over here, going back to this graph again, are going to have a value of f double prime. They're going to tell us how f prime is increasing, and in a case of concave up, the endpoints are going to have a positive value. There's nothing wrong with that. However, there's also a really nice argument to say that we don't include them because endpoints can't actually have curviness because they're just the point at the end, and in order to measure curviness, in order to measure increasing, decreasing, we need to have a comparable point on the outside, so we don't have that, so you don't include them either. But again, long story short, it doesn't matter. So whatever you prefer, this problem says use open intervals, so I'll use parentheses. Determine the open intervals on which this graph is concave up and concave down. Use a sign chart to help you justify. Well, that is kind of a lie because we can't actually reference a sign chart, but it still can help us phrase our justification. So let's rock and roll. First step, derivative. It's calculus, shouldn't shock you. 4 times 3 looks like 12x cubed, minus 3 times 4, that's 12x squared. 2 times 6, that's another 12x, very exciting, and then 12. Okay, so we have a million 12s here. Love that. Don't factor. And the reason I'm saying don't factor is we need to take another derivative, and factoring is just going to make your life one step harder. So, second derivative. This tells us about our concavity. 3 times 12, 36, 24, 12. Now we can factor. So f double prime, what do these have in common? I think 12 is common to all of them, isn't it? 3x squared minus 2x minus 1. The dreaded factoring when the value in front of x squared isn't 1. Who wrote this problem? I did, sorry. Don't forget that this is an easy guess and check, because there's only one way that we're going to make 3x squared. That's by using 3x and x. Only two ways to set up negative 1. It's either negative 1, positive 1, or vice versa. If I try this, this is 3x minus 1x would be positive 2x, but I want a negative up here, so I think we just need to switch this, which is an easy 1 erase and then put a plus. This is negative 3x plus 1 is negative 2x. We factored. I'm proud of us. All right, just like what we did for our sign chart for f prime, the next step is we find these, I'm going to say air quote, critical points. They actually have a different name when we do f double prime, but that's okay. So here we go. We're going to set this equal to 0 or figure out where this is undefined. This is a polynomial though, so f double prime is never undefined. I always like to write it and then cross it out. It's good to consider it. Setting this equal to 0, I imagine you guys are getting pretty good at this by now. You can probably just skip to the answer. As soon as you set this up, just go right to the answer. However, I'm being a friendly human and showing more steps in the video. I have had the question a couple times the last few days, wait, what do we do with the 12? Do we distribute it into one of them, both of them? Well, first, you definitely do not distribute it to both of them. You'll get the wrong answer then. You'll put in 144 instead of 12. To answer the question you were actually asking, though, how does the 12 affect the answer? The answer is it doesn't. If you distribute the 12 into one of these, and then you isolate x, you're going to have to divide by 12 at the very end, so it's just going to pop back out. The other way that we teach our Algebra 1 students is that these are all factors. There's 3 factors, so you could set all 3 of these equal to 0 if you wanted. Right? That's totally an allowable step. 12 equals 0 doesn't have any solution, so we can exclude it. And so if that makes you feel better of like, ha, I used the 12, that's fine. But honestly, most people would just skip to here, they'd ignore the 12, and we'd be fine. All right, negative 1/3, positive 1. Sweet. Are we done? No, we want to figure out where this graph is concave up or concave down. So, sign chart. Okay. We discussed how f double prime is going to measure the concavity. So therefore, in our sign chart, and we'll use that as a straight edge. Perfect. Negative infinity to infinity. We weren't given endpoints here. And then we have our negative 1/3. That makes our concavity 0. And 1. That also makes our concavity 0. We need to look at the signs of f double prime this time. Okay, well, let's check out the concavity from negative 1/3 to negative infinity. It seems like negative 1 is on that interval, so we should probably check that. Again, I will use the factored form. Someone else asked, well, wait, do we want to include the 12 there? Which factored form do we use? Well, all 3 of them get you the same answer. Honestly, when I'm checking, I would exclude the 12 because 12 is always positive. And if you do a positive times these, I don't think the positive is going to throw off your answer. So really, I'm just going to substitute negative 1 into the 2 factors and then look at the signs. So as we're going through and doing this, we have 3 times negative 1 plus 1, and then negative 1 minus 1. So I'm looking at negative 3 plus 1. That looks like negative 2 times negative 2. Negative times a negative. This is going to be positive. Cool. Looking at a couple more, we can tackle this one over here. I think 0 is a pretty easy one in this interval, isn't it? Yeah, 0 is smaller than 1, greater than negative 1/3. Substituting in 0 here, can we see that this is going to be positive? This is going to be negative, so we end up with a negative. And then we should probably try 2. Positive, positive if we try 2, so our last interval is positive. Now, looking at all of this, don't draw in increasing, decreasing, increasing, because that's not what f double prime measures. What f double prime measures is the concavity. And I have a second type of symbol that I like to use for concavity just to keep everything straight for you. I use the generic concave up and concave down graphs. So if f double prime returns a positive value, that means that my original graph, f of x, that I'm looking up here in purple, is concave up for this first part. If we return a negative value, we are concave down. And if we return a positive value, we're concave up. So I draw right side up and upside down parabolas to illustrate this fact. Okay, well, last part is we actually do need to put an answer here because the question asked determine the intervals where f is concave up and concave down, and the conclusion is very similar to f prime for our increasing, decreasing, so let's try it. We would say f of x, we always want to answer the question they asked about f of x, is concave up. CU is very common for concave up, though you should probably write it out if you have the time. I'm just out of space here. Is concave up on negative infinity to negative 1/3, and I'm doing open intervals, parentheses, because they asked us to do that, right? And 1 to infinity, because, well, how do we know that? How do we know to draw right side up parabolas? Because the sign of f double prime is positive. So because f double prime of x is positive, greater than 0 is positive, right? And then I imagine you could write the conclusion for our concave down. It's no different, right? We would just say, and I'm out of room, so I'll just verbalize that. F of x is concave down on the interval from negative 1/3 to 1 because f double prime is negative. And that's that. I did mention earlier that when we set f double prime equal to 0 and find these guys, they have a slightly different name. They're no longer known as critical points. Critical points are pretty explicitly defined as the places, the locations on a graph where the slope is 0 or undefined. And I didn't find where the slope is 0 or undefined. In fact, on this graph up here, it's my guess that the slope is not 0 or undefined. And I do have the graph ready to go, so let's take a peek. Let's remember these couple intervals and see how we did here. So if I look at my graph, here we go. I have it in purple. You'll notice it appears to be concave up until, oh, not until here, right? Not until -1. It's concave up until, when did we say it was concave up until? I think we said -1/3, didn't we? And then it should be concave down from -1/3 to 1. So -1/3 is somewhere right in here, 0.333. Right, so it's pretty tough to see, and Desmos isn't actually going to pull this out for us, but that's approximately -1/3. So that's telling us from this point to the left is where our graph is concave up. But then from here until -1, which we can see over here, I'm sorry, from here until +1, right, our graph is concave down. You can kind of see that downward parabolic shape right here. That's the concave down piece, but it's pretty hard to pick out where we changed from concave up to concave down, except at this point, doesn't the graph look pretty linear here, right? Doesn't it look like a line which has 0 concavity? So we had positive concavity, F double prime positive, 0 concavity, now we're negative, until right here, and then this one's a really nice change of concavity. And then we go upwards, right? Concave up from 1 out to infinity. Looking at f prime, which we weren't asked to do here, but we can do, we notice that f prime is 0. There's 0 slope here. This is a critical point. And it looks like we have one more critical point, which is right here. In fact, this critical point looks like it's both a place where our graph changes concavity and there's a slope of 0. They don't always overlap, though. I mean, -1/3 definitely doesn't have 0 slope. You can see it has positive slope, a positive derivative. So be careful confusing or mixing up those two, but we'll get plenty of practice. All right. Now, going back to what these guys are called, the x value where a graph changes concavity is known as a point of inflection. Now, when something inflects, it bends, right? Sometimes you'll hear inflections in your voice. Some people's voice will inflect and get really high or inflect and get really low. Sometimes when they're surprised, that's an inflection point in your voice. These bends, these points of inflection happen a lot when you're talking about metal as well. Metal can inflect or bend somewhere. Don't forget that when f prime of x equaled 0 was undefined, we of course referred to these x values as critical points. This is not quite the same as the second derivative. When f double prime equals 0 is undefined, we say these x values are potential points of inflection. So these guys up here are potential, which I promptly misspelled, potential points of inflection. POI is a very common way to abbreviate point of inflection for obvious reasons. However, I cannot call them inflection points until we can prove that f double prime of x changes sign at those points. So once I've made a sign chart and I'm pretty positive that f double prime changed sign there, now they actually become real inflection points, points of inflection. But over here, without a sign chart, we cannot refer to them as actual inflection points. We need to make sure that f double prime changes sign. And so you're like, well, what does that look like if they don't change sign? Well, let's try one. Find and justify all points of inflection for g of x equals this weird thing. And then check your answers on your calculator. We're going to check on Desmos and by looking at that graph. So yeah, go ahead, try the exact same steps that we did on the previous page. Once you're done, unpause, and we'll see how you did. All right, so running through this quickly since you just had time to work on it, g prime makes this look like it's going to turn out terribly because 4 times 2 becomes 8/3 x cubed, and you're like, ew, what have you done to me, plus 2, right? However, g double prime is much nicer, isn't it? Because the 3 is going to cancel out the 3. It's going to give us 8x squared plus 0, which I'll leave off. Cool. Let's look for potential inflection points. That's where g double prime is 0 or g double prime does not exist. It's a polynomial. G double prime exists everywhere. So we should probably look for g double prime equal to 0. Easy enough. 8x squared equals 0. I'd say just divide by 8 and take the square root. Yeah, we get x equals 0. Now, this is a very common type of problem where the multiple choice especially will try and set you up and say, find the inflection points. And people will go, ooh, inflection points, that's just like critical points, except we use the second derivative instead of the first. So they'll do this, they'll find 0, 0 will be a multiple choice answer, they'll circle it and go, haha, I'm a winner. But unfortunately, in this case, you are not a winner. You're almost a winner, but not quite there. Much in the same way that this is almost an inflection point, but not quite there, right? This is a potential point of inflection. How do we determine if it's actually a point of inflection? Well, we draw a sign chart. So quick sign chart. This one's pretty easy. There's only one potential inflection point, okay, and that is at an x of 0. When x is 0, that causes g double prime to be 0, right? Of course, if you substitute this in here, we get 0. But we do need to check it. So let's remember that our g double prime function is this guy over here, and I will try a couple values in there. So let's try a negative value. So I'll do -1, that's between 0 and infinity. So we get 8 times -1 squared, positive 8, isn't it? And then let's also try positive 1. Well, that's 8 times 1 squared, which is 8. Positive, positive. This means that my graph is concave up and then continues being concave up. In fact, when they're right next to each other, I like to just draw it all the way across to show that it is concave up everywhere. And so the question becomes, did g double prime change sign at 0? And the answer is no, it stayed positive on either side. We did go to 0 concavity here. The graph was perfectly flat. It was probably linear there, but it didn't change sign. So how do we justify this? Well, we say g of x, not g double prime, right? They asked us about g of x, has no points of inflection because g double prime of x never changes sign. And that's easy enough. So again, the difficulty or the increased burden of proof on a point of inflection versus a critical point is if this was g prime and they said find critical points, that's a critical point. However, this is g double prime, and we need to check to make sure g double prime changes sign. What does the graph look like? It's actually kind of an interesting looking graph here. Something like this, right? It's pretty wild looking. So the point that we were just talking about at 0, right? We were definitely concave up, concave up, concave up. Right at 0, we're concave up on this side and also concave up here. At 0, though, look how linear this function looks. Doesn't it look like a perfect line? And in fact, we would argue that at 0, it is a wonderfully diagonal line, which is why there is no curviness, no concavity here. Okay, but it definitely is not a changing concavity because we are concave up and we continue being concave up. Alrighty, last problem. This problem is a little bit intense and you want to write small. And the reason it's a little intense is because it asks you to do something that is a pretty common multiple choice question, and it actually shows up on free responses as well. This one is more intense than a regular free response or multiple choice because I picked a function that I think we're probably not as used to working with, sine of 2x. And I know a lot of my students get worried when there's that extra coefficient on the inside. It does make it a little more challenging to solve. So we're going to run back through that, and also this problem is different too because the problem says if it just said find the interval where the graph is concave up, you could do that, right? Concave up, that's the second derivative, inflection points, make a sign chart. However, what if they also said, which they do, find and justify any interval where f is decreasing? Increasing, decreasing. That brings us back to the first derivative. And so on this problem, I think we're actually going to have to look at a double sign chart. We're going to have to look at a sign chart for f prime and for f double prime. So I'm going to do the sign charts at the end, and I'm going to do all the groundwork for f prime and f double prime, and I'm going to try to keep my colors going on first. So I'm going to start with, because f prime we get to first, I'll do an orange. I'm going to start with the increasing, decreasing part. So here we go. F prime of x. Well, the derivative of sine is cosine. And then we have to multiply by the derivative of the inside, which is 2. So probably most commonly written as 2 cosine of 2x. We need to find critical points here. So where is f prime equal to 0 or undefined? Okay. And only from 0 to 2 pi, which is actually kind of nice because we should know that our cosine and sines have infinite answers. They just oscillate back and forth, right? So it's nice that we get to restrict our answers. Okay, well, how do we do that? Well, it's never undefined. That's nice. Trig function, continuous, easy peasy. This one, though, is a little trickier. So 2 cosine of 2x equals 0. And I think we can also probably divide off the 2, right, and just say it's cosine of 2x. And then I know students get trigger happy here and they say, ooh, can't we undo cosine with inverse cosine of both sides? You can. However, inverse cosine, whenever you put that in, can only give one answer. It's a function. Functions only give one output for an input. And so you're just going to get one answer here. But it turns out cosine of 2x has several answers, which really is a bummer for you guys. So how do we do it? Well, I always bring it back to a u substitution. This is how I teach it in trig as well. So I'm going to say we're going to let u equal to 2x. Okay, so that becomes cosine of u equals 0. And this we need to know at this point. And if you're not sure, I can draw a nice little, and I'm going to erase this, so you might want to draw it somewhere else. You can draw your unit circle. We're going to be dealing with these quadrantal angles today, so I'll leave this up for a bit, but I will end up erasing it. 1 comma 0, right? We move right 1 up 0, 0, 1, negative 1, 0, and 0, negative 1. And then we think about rotations. And in fact, we're dealing with cosine here, so don't forget, we'll do it in purple, that's fine. Don't forget that cosine is the x value, right? So looking at these guys over here, I think we can see that cosine is 0 at pi over 2. And then we go, and I probably shouldn't have done that, we should start here. So it's going to say it's at pi over 2, and then we move 180 degrees, and that gets us to 3 pi over 2, and then we move another 180 degrees, 3, 4, that gives me 5 pi over 2. It's really odd multiples of pi over 2, but a nice way to put that is we can say this happens every 180 or every pi rotations from pi over 2. So u is pi over 2 plus pi k rotations, right? It repeats every 180 degrees. Of course, we weren't actually solving for u, I don't think, were we? U is actually 2x here. So we would say, okay, cool. 2x is equal to pi over 2 plus pi k. And then we should probably divide out that 2. So instead of dividing by 2, maybe think of multiplying everything by 1/2. That might make your life a little bit easier, right? So we end up with x equals distributing the 1/2 pi over 4 plus pi over 2 k. That's awesome. Let's go ahead and find all of our values that occur from 0 to 2 pi. And we do that by just picking values of k starting at 0, right? We want to rotate forward. Negatives will take us backwards starting at 0 and seeing what your x values are. So if I replace k with 0, that cancels, and it just leaves us with pi over 4. Cool. If I replace k with 1, ooh, this might be easier with common denominators, huh? Let's multiply top and bottom by 2. We end up with something like this. I can make mine a little bit nicer, like that. Okay, so let's say k is 1. If k is 1, this just becomes 2 pi over 4. 2 pi over 4 plus pi over 4 is 3 pi over 4, right? We had 1 here, and now we moved over here, okay? When k is 2, 2 times 2 is 4. 4 pi over 4 plus 1 more is 5 pi over 4. And I bet you see the pattern now. The last one is going to be 7 pi over 4. Okay, we don't need to go any further than that because once we go here, here, and here, the next one's going to be 9 pi over 4. And 9 pi over 4 is greater than 2 pi. Okay, so I have found all the critical points for the original, for f prime. Cool. Now, the problem, though, is we also need to find the potential points of inflection, and that's the part that I'm going to do in green. Take a look at this. You might notice that cosine is 0. You might notice that sine is 0 at 0 and pi and 2 pi. So it's very, very similar to this, and so I'm going to go a bunch faster. If you need more help, you can always reach out to me, but let's go ahead and take care of that second derivative. So, second derivative, I need to take the derivative of this guy, so f double prime of x. The 2 stays where it is. Derivative of cosine is negative sine of 2x times the derivative of the inside. So I think that gives me, and I'll work down below, f double prime of x is going to equal negative 4 sine of 2x. Setting f double prime equal to 0, or determining where f double prime does not exist, I think isn't too terrible, because we need to set this negative 4 sine of 2x equal to 0. I should zoom in here, sorry. Dividing by -4 just cancels that out. Sine of 2x is really going to be the exact same thing that we did before. You can let u equal to 2x. You're going to get sine of u equals 0. Sine equals 0 at 0 plus pi k this time. So we can show that step. It's going to equal 0 plus pi k. When we do the substitution, 2x, and then multiply both sides by a half, we're going to get our actual value that x is equal to 0 plus pi over 2k. And then when we start plugging in values for k, it gets a lot easier. We get 0, pi over 2, and then we get 2, which is 2 pi over 2, which is really just pi. And then we plug in one more, and this gives us 3 pi over 2. And then even one more, I think we get to 4 pi over 2, which is 2 pi, which we are going to include because we have this closed bracket here. Oh, that was a lot of trig. Sorry for all of that, but it is good to keep that trig fresh in your brain. You'll notice that I try to factor and do trig at least once every class. I find those are the two biggest holes my students have in their memories in terms of algebra and trig skills. So we have these two. Are we done? No, sadly not. I'm almost out of room here, but I think I can make this work, especially by zooming in. You guys might want to write pretty darn small or start another piece of paper. I apologize for the lack of space. You might have noticed that I started to draw a very large sine chart, and there's a reason for that, because this is going to be a double sine chart. Bam! We need to both look at the signs of f prime of x, which I've done in orangish yellow, and also the signs of f double prime of x, which I've done in green. Now, the big issue here is I have like a billion points here because mostly I didn't think this problem out very well. I really should have just done x, but 2x seems so tempting. So let's see what we can do. We are going from 0 to 2 pi. And we have a whole bunch of points in between. And it may help you to think about just a unit circle as you move around here, so we can see what goes in order. I think we can tell that pi over 4 is going to come first, and then pi over 2, and then 3 pi over 4. It looks like we're really just alternating back and forth between these. So I think that will probably be all right. And I'll try to keep the colors going too. So I think pi over 4 comes first, right? And that is when f prime is 0. Then we have pi over 2, and that is when f double prime is 0. And then back and forth, right? Now we have 3 pi over 4. What are the odds I run out of room here? Probably pretty good. And then, of course, we have pi. Come on, Mr. Grant, write smaller. Pi is halfway there, though, and that is kind of about halfway across my number line. That's looking pretty good. And then we, I think, need to go to 5 pi over 4, something like this. Okay. And then we have 3 pi over 2. I think I'll make it. And then we go to 7 pi over 4. Ha! And then we marvel in awe at my partitioning skills, because that was pretty darn good, and I'm proud of myself. Whew. Okay, now what? Well, now we actually have to plug values in on all of these intervals, which is a bummer. Oh man, because now we need to try numbers in between and plug them into our original functions here and, where did that go? Over here. Definitely going to take a bit of work here, but shouldn't be too terrible. In fact, you already have some pretty nice values to plug in, just sitting over the intervals, right? So if I want to do f double prime first, why not? It's sitting up here, nothing to be too terrible. I think maybe the value I can plug in that's on this interval from 0 to pi over 2, why don't we just try pi over 4? I mean, it's on that interval. It's not a bad thing to do, right? So I'm going to try pi over 4 up here. Okay. Now, the nice part is when you try that pi over 4, again, we're not looking for an answer. We just need to know if this is positive or negative. So it's -4, that's a negative. These cancel and become pi over 2. And we need to know that sine of pi over 2 is positive 1. So we get a negative times a positive. This ends up being a negative. So my first piece down here is negative. And then I'll just keep going through the rest of these. So the next one I'm going to try is 3 pi over 4 for this interval. Okay, so 2 times 3 pi over 4. This becomes a 2. Sine of 3 pi over 2 is -1, so this becomes a positive, right? Because we have a negative times a negative. And then we'll just continue on through. So 5 pi over 4, substituting in here, 2 times 5 pi over 4. And this becomes 1 and a 2. Sine of 5 pi over 2, where the heck is that? 1, 2, 3, 4, 5 pi over 2. That's the same as pi over 2. Oh, are we just repeating again? That's awesome, because if we're just repeating again, then this has a very predictable pattern. Sweet. Let's go ahead and look at f prime of x then, and we're going to do the exact same thing. When we're substituting in f prime, I'm going to skip this little mini interval at the beginning, and I'm hoping I can establish a pattern just to fill it in. And let's go ahead and just use this guy and plug it into f prime. So just give myself a little room here. If I'm using f prime, or f prime of x, or sorry, I should actually use the value, we're going to plug in pi over 2 here, and it's 2 times the cosine of pi over 2. Cosine of 2 times pi over 2. There we go. These cancel. We get that cosine of pi, which is -1, and so we end up with a negative value on the first interval. Let's try pi next. So it becomes cosine of 2 times pi. Cosine of 2 pi is 1. 2 times 1 is positive. Sweet. 3 pi over 2. See, we're getting pretty good at this. Assuming I haven't left you too much in the dust. Cosine of 3 pi. 1 pi. 2 pi, 3 pi is a negative value, so 2 times -1 is negative. Can we see the pattern here? I think it goes positive, negative all the way through. That is awesome. Okay, now what the heck did this question ask us to do? Find and justify intervals where the graph of f of x of sine of x is both concave up and decreasing. Okay, well, concave up, whoops. Let's go ahead and do this in the color I wanted to do it in. Concave up is where f double prime is positive. Decreasing is where f prime is negative. So I think the question is then, is there any interval here that overlaps? Well, and hopefully you're noticing that this negative portion right here overlaps with this portion down below. And that from pi over 2 to 3 pi over 4 is a portion of f where f prime is negative, f double prime is positive, so decreasing and concave up. Is there anywhere else? Yeah, I think I see one more piece over here. And it looks like we're going from 3 pi over 2 to 7 pi over 4. Great. I think we have our interval then. The intervals aren't too tough to justify. You can use open or closed, whatever sounds good to you. But we do something like this. We'd say f, remember we're talking about the original graph, is both concave up and decreasing on the intervals pi over 2 to 3 pi over 4 and 3 pi over 2 to 7 pi over 4. So we've now stated the intervals from our sign chart, but we do need to explain why. So because f prime of x, well, what was f prime on those? Is negative, and f double prime of x is positive on those intervals. And again, we're not going to say that f prime is increasing. No, we're reading the signs from our sign chart. F prime is negative and f double prime is positive on those intervals. And that's great. Now again, this problem was much more complex than anything you're going to see. It takes way more time because of that 2x inside. It would be much easier if you saw something with, say, sine of x, which you might see on your homework. But it is very common for them to ask about two different things at once to make sure you know the difference between the first derivative and the second derivative. So thank you as always for hanging out with me. Today we learned about concavity, or the flexiness of a function, the curvature of a function. We learned about points of inflection, which is where f double prime changes sign, where our graph changes concavity. Next class, we're going to come back and we're going to hit the second derivative test, which is, of course, very similar to the first derivative test. So keep it up. Reach out with any questions. Please let me know what mistakes I make, and I'm fixing them as you guys post on my videos too. So thank you so much for that, and enjoy your day.